this homework help video, I'll go through how to apply the method of hypothesis testing to the standard normal distribution. These are the cases in which you have an a priori mean that you know, and along with that you have a standard deviation that you know. This is just a summary of the previous lecture. If you remember, there's two kinds of tests. There's the two-tailed test, in which case the alternative hypothesis is written with a not equal to sign. There's a left where you have a less than sign, and a greater, and a right where you have using the greater than inequality. In all of these cases, you're assuming the normal standard distribution. This is 0 because these are z values, and you're going to reject either the left tail, the right tail, or both tails. An important parameter that you need to know are the critical values. The critical value is a z value sitting right at the edge between the critical and the non-critical region. And there's only three probabilities that we're going to work with: 10%, 5%, or 1%. These are the chances for making a type 1 error. And type 1 error is rejecting a null hypothesis when it's really true. That is convicting an innocent man. That's the type 1 error. Remember, type 2 errors have to do with the power of the test, and we don't compute them, and right now we're just leaving them alone. Okay, so depending on whether you are requiring a 10%, 5%, or 1% probability, alpha has the decimal equivalent to that. And from this sort of graph here, you can find the critical values without looking them up. They've already been looked up for you, and they're right here. If you have a two-tailed test, you're going to have two critical values, one on the right and one on the left, and that's why you have the plus and minus sign. If you only have a left-tailed test, you'll have values with negative sign. If you have a right-tailed test, you'll only have one value, and it will have a positive sign. They are different from the two-tailed test because when you have a left-tailed test, you have to take all of that area, which alpha represents, and put it in that tail. For the two-tailed test, you divided alpha by 2. So anyway, that's covered better in the lecture on the different kinds of tests. But now that you have the test set up, and you should sketch what you're doing, that helps a lot. So you make a sketch of it. For example, if you had a right-tailed test, you might have a sketch that looks like this, hopefully better than that. Here's your critical value right here, and this is the tail that's the critical region. Then you've done a test and determined a k value. It's probably the mean from a sampling, a group of whatever unit subject that you're working with. And there was a certain size to that sampling, which is n. Now in this case, you happen to know you had an initial assumption for the average, which is mu, and you also knew the standard deviation. You assumed that not only did you know the average, but the distribution is bell-shaped, and you also knew the standard deviation for it. Okay, so in that case, you compute a z-value using this formula, which is the same formula that you used for confidence intervals. I'll do this example. The one for the homework is so similar that there'd be no work to transpose it. Okay, in the other lecture I was talking about, say you had to do a test and you were measuring heights of some children. You're working in some kind of pediatric clinic. You can look online and you can find the World Health Organization's average height. So their average height for a 4-year-old girl, girls and boys different height, but the average height for the 4-year-old girl was 102.3 centimeters. And there's also a standard deviation of 4.3075. So in this case, we know the a priori value is the average that we, either the advertised average or previously measured average. So in this case, it'd be 102.73 would be the value of mu. Also, we know the standard deviation for the population, and it's 4.3075. Okay, now a sampling was done of 30 local children. All right, 30. Should have said girls here so that it would match up, but that's okay. So you measure the heights of these 30 of these kids. That means your sample size is 30, so n is 30. And when you measured all these, you came up with a mean height of 103.601. All right, that's pretty close to 102, but maybe it's not. Maybe it shows a trend. Maybe it's statistically different. And that's why you use the hypothesis testing. So there's all your data, and that's what you would write down, or something similar, of course, to the first question in that homework. Now, we're going to do a two-tail test. So this question says, state the null hypothesis. The null hypothesis says that nothing changed. Oops, 7.3. The average is still the same as what was originally presented, 102.73 in this case. The alternative hypothesis for a two-tail test is that it's different. Obviously, in this case, you could do a right-tail test and say that it's greater than, but I want you to do a two-tail test. So that's how you state the null hypothesis. Nothing changes. For the alternative hypothesis, use a not equal to sign. Now proceeding along through the questions and the homework, the idea is to use a 10% probability. You don't get to pick it, the question picked it. So if it's a 10% probability, then alpha equals 0.10. And now you have to find the critical values. And to do that, you go back and look at the tables either in the book or in the lecture notes. So you go back to the chart here, or again, you can use the book too. And this is a two-tail test, and alpha was 0.10, so we need the critical values, and they're given right here, plus and minus 1.65. Oops, this got erased. So we have alpha is 0.10 because of that probability, and the critical values were plus or minus 1.65. Okay, now we have to take the k value, the measured value, and turn it into a z value. We're going to do that using this expression, which is given in the homework too. So k, the test measurement, test average was 103.601. The World Health Organization published value was 102.73. Subtract those, and then you divide by the standard deviation, and that is divided by the square root of the number in the sample. All right, if you want to, this is one of those complex fractions the way it's written. If you want to use your calculator, you can do the first part pretty easy, 103.601 minus 0.73, and get an answer. Then you have to have the answer, and then put the divide sign, use parentheses. Otherwise, you might get the wrong answer, or do this calculation separately. Actually, the result of this complex fraction is this. Because this fraction, actually the 30, is really flipped upstairs. So you can do it that way, but if you don't use parentheses, or you aren't careful with your calculator, you'll get the square root of 30, you'll get that in the wrong place. Okay, at any rate, assume I did this right, and I got an answer here of 1.1074. All right, the critical values were plus or minus 1.65. So this value is in the non-critical region, and the conclusion is to accept the null hypothesis. That means even though your measurements looked like the people in your local area were a little bit different or taller than the average, it's not statistically significant. Then the next step, or somewhere along the line, the step is to do this graphically. So these are z values, okay, and the critical values were plus or minus 1.65. Okay, so 1.65 is about here. Maybe here, okay. minus 1.65 is about here. Whoa. No, that's not right. Let me erase that. Okay, now I can try to draw it in the right place. Minus 1.65 is over here and here, because it's symmetric. Here are these tails. So alpha was 0.10. The area in these tails, 0.05 of the area under the curve is here. Another 5% is out here. Here's a critical value, 1.65. Here's the other critical value, minus 1.65. The measurement, the K, turned into a z-score, is 1.1 something. It's right here. So it's in this region, which is the non-critical region, which just says that though you measure something a little bit different, it is not statistically different. It's not different enough to really think that that we have to challenge the initial assumption.